Good morning. Today we'll be talking about adversarial techniques for face recognition models.
In the last decade, deep learning and machine learning technologies have been groundbreaking and have brought a wide range of applications that were extremely tedious and complex to implement. One of these applications is face recognition. Face recognition recognizes the identity of a person using their face. It analyzes facial details and patterns to effectively verify and single out an individual. Face recognition is applied on identification, authentication, and detection tasks in domains such as security, law enforcement, health, marketing, retail, and many others. However, as with many deep learning models, face recognition models are vulnerable to adversarial attacks. Inputs to machine learning models that an attacker has intentionally designed to cause the model to make a mistake. Filters or other alterations can be applied to the images before being fed to the model, which can then cause faces to be misclassified or not recognized at all. Thus, it is critical for face recognition applications, specifically those involved in security and authentication, to be robust enough to resist the adversarial attacks. We propose to develop an adversarial learning framework targeted to face recognition models. We want to research the most popular and effective face recognition models and algorithms, the data with which they operate, and the existing adversarial attacks to downgrade the performance of such models. There are many adversarial attacks targeted to computer vision models which we can use as an inspiration for creating attacks for face recognition tasks. Numerous attacks against these face recognition models have been already created, but many are too complex to implement on a higher scale. We aim to understand how face recognition works, which features it uses to learn, and see what we can use to develop efficient attacks. Adversarial attacks are useful to identify the vulnerabilities of the models before they are deployed.
This project will be divided into three stages, being the first one for literary review, the second stage to develop various adversarial attacks, and the last stage to compare and benchmark the different FR models with all the attacks.
For those of us that joined the project this year, we had a lot of learning to do before we got started on our research. We started by taking Coursera's Introductory Machine Learning course by Andrew Ng, which went in depth into all the math behind common machine learning models. We had group meetings where we discussed what we had learned in order to help ourselves understand the concepts better. Once we completed the course, we moved on to learning about adversarial learning with the help of Dr. Pedro Torres.
Fast gradient sign method. This method attacks the neural network using gradient to create contradictory examples. For any input image that is manipulated, the method uses the loss gradient relative to the input image to create a new image that maximizes the loss by altering the epsilon, either by increasing it or degrading it. The formula is this new adversarial image equal to the original input image plus the epsilon multiplied by this loss gradient relative. In this example, we can see the Labrador, which is our original input image, and adding a epsilon with the noise, we can see the computer is detecting other things that is not the Labrador.
The one pixel attack is a black box attack that takes an image and changes its classifier label by only altering one pixel. It has been shown that this can be quite effective on images with a lower resolution, and it can also be applied on images with a larger resolution, but it will be less effective. The attack can also be scaled to alter multiple pixels, but this also means that it makes it easier to spot the adversary images by a human eye.
The basic idea of the BLA attack is to reject perturbations based on the visible light spectrum in order to carry out a targeted or untargeted misclassification in face recognition models. The motivation for this attack is the difference between human eyes and digital cameras, specifically the persistence of vision. To ensure the discretion of these attacks, The BLF process is broken down into two frames, one designed to change the characteristics of the current user, called a perturbance frame, while the other frame is used to hide the disturbance frame from human eyes, called a concealment frame, both of these based on chromatic addition rules.
Add faces is an automated face synthesis method comprised of a generator G, a discriminator D, and a face matcher F. It works for targeted and untargeted attacks. In essence, given a probe face image, the attack automatically generates an adversarial mask that is then added to the given probe in order to obtain the adversarial example. The overall objective function consists of three losses: the generative adversarial network or GAN loss for the discriminator, the identity loss for evading face matchers, which determines the attack success, and a perturbation hinge loss for bounding the magnitude of the adversarial mask, which determines how different the image looks from the original.
The semantic adversarial attack consists on applying parametric generative transformations combining previous generative architectures such as fader networks and attribute GANs. On this approach, the original image is compressed into a smaller latent space and added the adversarial attribute vector. Later, the semantic representation of the attribute and the original image are transformed into what will be the adversarial example.
RL optimization consists of applying generative reinforcement learning techniques to generalize the behavior of a face recognition model and generate an adversarial neighbor to alter the output of the AFR model. With this technique, we can consider the FR model and black box environment and optimize the generator based on the state reward pair when interacting with the model.